Welcome back to the course Rocket Propulsion offered by Adult Systems. In today's class, we will discuss about liquid propellant rocket engines. So the index for today's class, so the contents what we will see is first is background of liquid propellant rocket engines. That is, we will discuss some of the fundamentals, basics of liquid propellant rocket engines. Then we will discuss types of liquid propellants which are available and its various classification. Then we will cover some of the safety and environmental concerns of this liquid propellant rocket engines, heading to propellant tanks and feed systems. So what kind of tanks and what kind of feed systems are used in liquid propellant rocket engines. Then we will discuss about the combustion process. So how this combustion is initiated and how it works in different zones for a liquid propellant rocket engine. We will discuss it in detail. And lastly, we will discuss some of the combustion instabilities which are present, which are created because of the combustion process itself and how we can control this instability. So we will discuss all of these topics in this course. So let's begin. So first we will start with background of liquid propellant rocket engine. So as discussed in the previous video about fundamentals of rocket engines, we have seen what are solid propellant rocket engines and what are liquid propellant rocket engines. Liquid propellant rocket engines are the type of chemical rocket engines where propellants used are in liquid form. So the main fuel and oxidizer which are used for such rocket engines, they are present in liquid form. So the liquid propellants, which are the working substances of rocket engines, constitute the fluid that undergoes chemical and thermodynamic changes. So this fuel and oxidizer are then mixed together in the thrust chamber and then ignition is given such that the combustion happens and then the exhaust velocities are expanded in the supersonic noise. The liquid oxidizer and the liquid fuel, they are stored in different propellant storage tanks as we can see in the figure, and then a feed system is used to allow this propellant to be fed into the thrust chamber using the valves and pipes. So now we can see that the term liquid propellant embraces all the various liquids used and may be one of the following. So the liquid propellant which is used in liquid propellant rocket engines, it may be an oxidizer like liquid oxygen, nitric acid, nitrogen tetroxide, etc. Or it may be a fuel, that is kerosene, alcohol, liquid hydrogen, etc. Or it may be a chemical compound or mixture of oxidizer and fuel ingredients which are capable of self-decomposition such as hydrazine, or it may be any of the above but with a gelling agent. So these are the new kind of propellants which are seen today but they have not yet flown. Still experiments are going on. So that's why they are used only rarely. So this is about the background of liquid propellant rocket engines. Now we will see what a liquid propellant rocket engine consists of. So the first thing, that is, it needs a thrust chamber where the combustion can happen. Then a feed mechanism for feeding the propellants from the tanks into the thrust chambers. So there are tanks in which the propellants are stored and the feed system is needed to supply these propellants to be expelled from the tanks till the thrust chamber. So feed mechanism is needed. Then power source to furnish the energy for the feed mechanism. A power source is needed for the feed system to work. Then suitable plumbing or piping to transfer the liquid propellants. Obviously, these propellants will be at very high pressure, so good and suitable plumbing or piping settings are needed. Then a structure to transmit the thrust force. So the thrust force which is created, a strong structure is needed to transmit this force. So a strong supersonic nozzle should be present. Then control devices including valves to start and stop and sometimes also vary the propellant flow and thus the thrust. So some control devices are needed to change some of the settings. Also there might be some applications where we will need thrust vector control systems, then random variable thrust feature, and engine condition monitoring or engine health monitoring subsystem, and various instrumentation measuring device. So this all things, the primary things are present in a liquid propellant rocket engine. So earlier also we have discussed some of the advantages and disadvantages of liquid propellant rocket engines. So here we will discuss some of them as well. The best advantage we can get from liquid propellants is it will give highest specific impulse but at the cost of complex design, because many parts and many components are involved. So if something goes wrong, then it will be very dangerous to tackle. Then such kind of rocket engines can be randomly throttled and randomly stopped or restarted, but there is a problem of spills or leaks for several propellants which can be hazardous, corrosive, toxic, and can cause fire as well. Then liquid propellant rocket engines can be designed for reuse after field services and checkout. Also the thrust chamber can be cooled by propellants and can be made lightweight. Also, most propellants have non-toxic exhaust which is environmentally acceptable, and with multiple engines can operate with one or more shutoff, that is engine out capability is available for liquid propellant rocket engines, which is not in solid propellant rocket engine. But the problem is that the tanks which we are using for propellant storing, to pressurize those we need a separate pressurization subsystem. Then sloshing in tank can cause a flight stability problem, which can be minimized with baffles. So these are the advantages and disadvantages for liquid propellant rocket engines. Now we will see the classification of liquid propellant rocket engines. So based on various parameters, there is a broad class of classification for these kind of rocket propulsion engines. So based on the mission, that is if we need to impart significant velocity to propel a vehicle along its flight path, or we need it for altitude control or some minor space maneuvers or trajectory corrections. Based on that, we can classify this liquid propellant rocket engines, or based on the application, whether we want to use it for booster stage and upper stage of launch vehicles, or for large missiles, spacecraft, or satellites, whether we need a high total impulse or low total impulse, or how much number of thrust chambers per engine are available, that is either 1 to 4 or 4 to 24. Then what thrust level we need, a high thrust level of around 4500 Newton to 79 lakh Newton, or a small range of around 0.001 to 4500 Newton. Then based on the feed systems, that is either turboprop, pressurized feed system with high pressure gas supply, or based on the cooling method, which may be propellant cooled or radiation cooled. Then based on the propellants, which is the most general and mostly used category, that is it may use a monopropellant, bipropellant, cold gas, cryogenics, storable, gelled or hybrid propellants. Then we have number of starts during a single mission. So based on how much starts there are available, also we can classify liquid rocket propellant engines. That is, there is either a no start, or sometimes there is one start, or several thousand starts for small thrusters. Then it may be classified based on shortest firing duration, that is, it may be fired for around 5 to 40 seconds, or even 0.02 seconds for small thrusters. And the last factor, that is how much life it is going to stay in space. So it may be hours, it may be days or months, or 10 years or more. So this is how the liquid propellant rocket engines can be classified of such several parameters, out of which we will discuss about the propellants which is highlighted into red. So we'll discuss different types of liquid propellants. So starting with what all propellants we have, that is monopropellant, bipropellant, cold gas propellant, then cryogenics, then storable, gelled and hybrid. So first we will see monopropellant. So it contains an oxidizing agent and combustible matter in a single substance. That is, it may be a mixture of several compounds, or it may be a homogeneous material such as hydrogen peroxide or hydrazine. So monopropellant is a single chemical compound in which an oxidizing agent and the combustible matter, that is the fuel, is present, and they are stable at ordinary atmosphere conditions but can decompose or yield hot gases when heated or catalyzed. So carrying a monopropellant is very advantageous because you don't need two different tanks. You can store this propellant with large quantity in one single tank, and you don't need a separate ignition system. You just have to catalyze it or heat it that it starts combustion. Then we have bipropellants. So bipropellants are two separate liquid propellants, an oxidizer and a fuel, and are the most common type. They are stored separately and are not mixed outside the combustion chamber. So monopropellants are the same, they are present in liquid form, but they are stored separately in different tanks, and they are not mixed together until they enter into the thrust chamber or the combustion chamber. A hypergolic bipropellant combination is self-igniting upon contact between the oxidizer and a fuel. So there are two categories under bipropellant, that is hypergolic or non-hypergolic. So a hypergolic is the combination of bipropellant in which the fuel and oxidizer, when they are mixed together, they can self-ignite. And non-hypergolic bipropellant combination needs energy to start its combustion. So these are the two basic types of bipropellants which are used in today's rocket engines. Then the next one, that is cold gas propellants, for example gaseous nitrogen or air, which is stored at ambient temperature but at very high pressures. It gives a low performance, allows a simple system, and is usually very reliable. It has been used for roll control and attitude control. Next we will see cryogenic propellants. So cryogenic propellant is liquefied gas at low temperature, that is liquid oxidizer, which is stored at minus 183 degrees Celsius, or liquid hydrogen, that is liquid fuel, which is stored at minus 253 degrees Celsius. So these cryogenic propellants are nothing but the cold gas propellants only, but they are stored at very low temperatures. So provisions for venting the storage tank and minimizing vaporization losses are necessary with this type of propellant. Next class is storable propellants, example nitric acid or gasoline. So such propellants are liquid at ambient temperature and at modest pressure and can be stored for long periods in sealed tanks. So such storable propellants are useful when they are going for a long mission in space. So space storable propellants are liquid in the environment of space. The storability depends on the specific tank design, thermal conditions, and tank pressure. Moving on to the next, that is gel propellant. So it is a thixotropic liquid with a gelling additive. It behaves like a jelly or thick paint. It will not spill or leak readily. So this is the greatest advantage of gel propellants, that they won't spill or they won't leak because they behave like a jelly. Jelly, how it is thick to our hand. The propellant is in such a form, they can flow under pressure, they can burn, and it is safer in some respects. So till now, gel propellants are being used for some experimental rocket engines only, and they have not been flown for commercial purpose. The last one, that is hybrid propellants, usually it has a liquid oxidizer and a solid fuel. So it is a very simple system where a liquid oxidizer is stored in a tank and the solid fuel is already present in the combustion chamber, and just the liquid fuel has to be fed directly to the thrust chamber and has to be ignited such that combustion happens. So various types of liquid propellants we have discussed now. We will see each of them in more detail. So first we will discuss about liquid monopropellants. So monopropellants, as we discussed, it contains an oxidizing agent and combustible matter in a single substance. Then it may be a mixture of several components as well, or it may be a homogeneous material. Some examples are hydrogen peroxide or hydrazine. Also, we have seen that monopropellants are stable at ordinary atmospheric conditions but decompose and yield hot gases when heated or catalyzed. The propellant fed and control system simplicity associated with the monopropellant make this type of propellant attractive for certain applications. So it can be used for some certain applications. Then hydrazine is being used extensively as a monopropellant in small altitude and trajectory control rockets for the control of satellites and other spacecraft, and also as a hot gas generator. So hydrazine has found its applications from very long back, and it has been used till now for some certain applications like small altitude and trajectory control rockets for control of satellites and other spacecrafts. So ignition of monopropellants can be achieved thermally either by electric or a flame heat or by a catalytic material. So we can use electric charge or thermal energy to ignite this monopropellants. So monopropellant must be chemically and thermally stable to ensure good liquid storage properties, and yet it must be easily decomposed and reactive to quickly give good combustion. So these are the properties which are needed for a monopropellant in liquid propellant rocket engines. Next, we will discuss about gaseous propellants. So cold gas propellants have been used successfully for reaction control systems, that is RCS, for more than 60 years. The word's cold gas, that is stored at ambient temperature, is distinguished from a warm gas which has been heated. And the engine system for this gaseous propellants is simple, which consists of one or more high pressure gas tanks, multiple simple nozzles, often aluminium or plastic, an electrical control valve with each nozzle, pressure regulator, and precisions for filling the venting gas. So some examples of gaseous propellants which are used is nitrogen, argon, dry air, krypton, and freon 14, which have been developed in spacecraft reaction control systems. So with using hydrogen or helium as cold gas with high pressure, the specific impulse is much higher, but the densities of such gases are much lower. Because of this, it requires a much larger gas storage volume and heavier high pressure tanks. So if the tank pressures are high, then maybe we can use a tank with a smaller size. Then the selection of the gas propellant, that is selection of a cold gas propellant, the storage tanks, the RCS design depend on many factors such as volume and mass of the storage tanks, the maximum thrust and total impulse which we need, the gas density which should be little high, then the duty cycles, required maneuvers, and flight duration. So based on these parameters, we can select a combination or we can select the gaseous propellants which we need for our application. Next, we will move on to gel propellants. So gel propellants, as discussed, have additives that make them thixotropic materials. They have the consistency of thick paint or jelly when at rest, but they liquefy and flow through pipes, valves, pumps, or injectors when an adequate shear stress is applied. So when they are at rest, they are in a thick form, but when they liquefy and they can flow through pipes, valves, pumps, or injectors when a suitable shear stress is applied. So the advantages of using such kind of gel propellants is that small aluminium fuel particles and inert solid particles can be suspended in the fuels and the liquid oxidizers, which will increase propellant density impulse, and thus reduce the size of tanks and vehicles. So we can increase the density of these gel propellants by putting some small aluminium fuel particles and inert solid particles in the fuels and liquid oxidizers. This way we can use the gel propellants by increasing the density, which will increase the density impulse, which in turn will reduce the size of the tanks and vehicles. So most gel fueled propellants are essentially non-flammable and will not usually sustain an open fire. So it becomes environment friendly. Then there is a reduced susceptibility of leakage or spill, reduced sloshing of liquids in the tanks, and the boil off rate is reduced. So again, it is a very good advantage upon the liquid propellants. Then short duration pushing has been tested. So yet the testing is going on and experiments are carried out on such propellants, but none of them have flown yet. Disadvantages are that there is a small decrease in specific impulse due to dilution with a gelling agent and less efficient atomization into small droplets due to high viscosity or less efficient combustion. For example, the characteristic velocity of oxygen kerosene propellant is decreased by 4 to 6% when the kerosene is gelled and aluminum is suspended in the fuel. So using the gelling agent can reduce the combustion efficiency by up to 4 to 6% for oxygen kerosene propellant combination. So the bubble free loading or unloading of propellants is somewhat more complex and may take longer. This is because residual propellant quantity will be slightly higher because the thixotropic fluid layer on the walls of the tanks and pipes will be thicker. So again, this may create a large problem for the rocket engine. Moving on to the next, we will discuss some of the liquid bipropellants, first oxidizers. So the most energetic oxidizer with the highest specific impulse is liquid fluorine. It has a high density and is extremely corrosive and toxic. Since it gives high specific impulse but at the same time it is extremely corrosive and toxic, it has been tested in several complete rocket engines but has been abandoned because of its hazards. So along with its good features, it has the limitations due to which it is not used in today's world. And some of the examples of liquid oxidizers are liquid oxygen, hydrogen peroxide, nitric acid, and nitrogen tetroxide. So we will discuss two of them, that is liquid oxygen and hydrogen peroxide. So liquid oxygen, which is often abbreviated as LOX, is widely used as an oxidizer and burns with a bright white yellow flame with most hydrocarbon fuels. So this LOX is used even today for many applications because it can be used as an oxidizer with most hydrocarbon fuels. It has been used in combinations with alcohols, jet fuels, kerosene type, gasoline, and hydrogen. So overall, it has a good compatibility with other many different liquid fuels. Then hydrogen peroxide is not only a powerful liquid oxidizer but also a clean burning monopropellant. In rocket applications, hydrogen peroxide has been used in a highly concentrated form of 70 to 99%. The remainder is mostly water. So the burning of hydrogen peroxide gives mostly water as a remainder. Moving on to the next, we will discuss some of the bipropellant liquid fuels. So many different chemicals have been proposed, investigated and tested as fuels. Only a few have been used in production rocket engines. So some of the examples of liquid fuels are hydrocarbon fuels, liquid hydrogen, hydrazine, unsymmetrical dimethyl hydrazine, monomethyl hydrazine. So we'll discuss two of them, that is some hydrocarbon fuels and liquid hydrogen. So hydrocarbon fuels, they are relatively easy to handle and there is an ample supply of these fuels available at relatively low cost. So the hydrocarbon fuels, we know that they are available in very good amount of supply and are relatively at low cost. A specifically refined petroleum product particularly suitable as a rocket propellant has been designated, which is called as RP1, that is rocket propellant number 1. It is basically a kerosene type fuel mixture of hydrocarbons with somewhat narrow range of densities and vapor pressure. So with some combinations, a hydrocarbon fuel, which is nothing but basically a kerosene type fuel mixture of hydrocarbon, which is called as RP1, that is rocket propellant number 1, and is particularly suitable because it has given some narrow range of densities and have a vapor pressure. Then moving on to the next is liquid hydrogen. So liquid hydrogen when burned with liquid fluorine or liquid oxygen gives a high performance. It also is an excellent regenerative coolant. So once ignited again, it can be used as a good coolant. With oxygen, it burns with a colorless flame. However, the shock waves in the plume may be visible. So the flame which is generated when it is burnt with oxygen, it gives a colorless flame, but shock waves are created which can be visible from the plume of the flame. Of all known fuels, liquid hydrogen is the lightest and the coolest. So we'll see why are these properties more important for some of the fuels and some of the oxidizers in the next slide, that is properties of liquid propellant. So it is very important to distinguish between the characteristics and properties of the liquid propellants, that is the fuel and oxidizer liquids in their unreacted condition when they are stored in the propellant tanks, and those of the hot gas mixture which results from the reaction in the combustion chamber. So it is very important to distinguish between these two characteristics when they are in their unreacted form and when the reaction of these constituents give us the exhaust mixture. So the chemical nature of the liquid propellant and the mixture ratio determine the properties and characteristics of both of these types. But unfortunately, none of the practical known propellants have all the desirable properties. So the propellants which we use today, they have some of the properties, but none of the practical known propellants have all the desirable properties. So the selection of the propellant combination is usually a compromise of various factors. So some of the factors are, first one is the economic factor, that is availability in quantity and a low cost are very important considerations in the selection of a propellant. That is correct because the propellant has to be available in large quantity and it should be available at a very low cost such that it can be affordable for many other organizations. And even the quality of the propellant matters which is available because it is usually more expensive to use a toxic or cryogenic propellant than a storable non-toxic one because it requires additional steps in the operation, more safety provisions, additional design features, longer checkout procedures prior to launch, and often being trained first. So if we use more costly or the toxic propellant, then we have to take care of these factors as well. And the next factor is the performance of propellant. So the rocket engine performance can be compared on the basis of the specific impulse, the exhaust velocity, the characteristics velocity, or other engine parameters. So there has to be taken a compromise between such parameters because the specific impulse and exhaust velocity are function of pressure ratio, specific heat ratio, combustion temperature, mixture ratio, and nuclear mass. The values of performance parameters for various propellant combinations can be calculated with a high degree of accuracy. So when dealing with selection of propellant combinations, so these performance parameters of the flight vehicle or the rocket engine has to be taken care of and some compromise has to be made between these quantities. Then the last factor which is very influential is the common physical hazards. So some of the common physical hazards which are associated with liquid propellants is corrosion, explosion, accidental spills, health hazards, material compatibility, etc. So although the several categories of hazards are described here, they do not all apply to every propellant or every bipropellant combination. The hazards are different for each specific propellant and must be carefully understood before working with the propellant. So these factors has to be taken care of or a compromise has to be made between these factors when we are selecting a propellant combination for a rocket engine. Moving on to the properties, that is, what are the desirable physical properties of a liquid propellant. So first, that is, it has to have low freezing point, which will permit us the operation of rockets in cold weather. Next, it should have high specific gravity because a denser propellant will provide a larger mass of propellants in a given vehicle tank volume. Then the third one, that is stability. So good chemical stability means no decomposition of liquid propellant during operation or storage, even at elevated temperatures. So the chemical component which we are using, it should be very much stable that it should not decompose during any operation or storage at any elevated temperature. Then the pumping properties, especially for the liquid propellants, that is, a low vapor pressure permits not only easier handling of the propellants but also a more effective pump design in applications where the propellant is pumped. So where we are using pump-fed propellants, a low vapor pressure propellant is much acknowledged and used. Next, heat transfer properties. So high specific heat, high thermal conductivity, and high boiling or decomposition temperature are desirable for propellants that are used for thrust chamber cooling. So these are the heat transfer properties for any liquid propellants which we are using. Then temperature variation of physical properties. The temperature variation of the physical properties of the liquid propellants should be small and should be very similar for the fuel and for the oxidizer. So the temperature variation based on the conditions, it should be small and it should be same for the fuel as well as for the oxidizer. Then some of the other properties are the ignition, combustion and flame properties. So all rocket propellants should be readily ignitable and have only a very short ignition time delay in order to reduce the potential explosion hazard during start. So all the liquid propellants should be readily ignitable and should have a very less ignition delay time. Then certain propellant combinations burn very smoothly without combustion vibration, which are gas pressure oscillation. So the combustion should be very smooth without any combustion vibration, which can cause some flight stability drop during its operation. The last one, that is flame properties. So smoke and brilliantly luminous exhaust flames are objectionable in certain military applications because they can be easily detected. So if a rocket is flying and smoke or a luminous flame is detected, then it is considered as objection in many military applications because it can be detected and destruction can happen if it enters any countryside's edge. These are the physical properties of liquid propellants. Now we will see how property variation and specifications can be done for some selective propellants to achieve the goal. So the propellant properties and quality must not vary from batch to batch because this can affect engine performance, combustion and physical or chemical properties. So there should be a similarity in the properties and the quality from batch to batch of the propellants which are manufactured. Then the same propellant must have the same composition, properties and storage or rocket operating characteristics if manufactured at different times or if made by different manufacturers. So even this has to be taken care of, that even if it is manufactured at different time or at a different manufacturer, then the propellants must have the same composition, same properties and storage or rocket operating characteristics. Also there are some features where we can alter some of the properties using the term called additives. So additives are used for altering and tailoring propellant properties. For example, to make a non-hypergolic fuel become a hypergolic, we can do is a reactive ingredient has to be added in the non-hypergolic fuel. This way we can alter some of the properties based on our need. So to increase the density or to alleviate certain combustion instabilities, a fine powder of heavy solid material such as aluminium can be suspended in the fuel. So to make it much denser, fine powder of heavy solid material such as aluminium can be suspended in the fuel. Then to lower the freezing point temperature, additives can be used. So the properties which we discussed earlier, we can alter these properties, that is we can make it more denser, we can make it more cool by using such additives. So these additives may be metals or non-metals. Moving on to the next slide, that is we will discuss some of the environmental and safety concerns which are for liquid propellant rocketing. So the safety and environmental concerns are the toxicity, explosiveness, fire or spill danger. So these are some of the safety concerns which are involved in liquid propellants. So before an operator, assembler, maintenance mechanic, supervisor or engineer is allowed to transfer or use a particular propellant, he or she should receive safety training in the particular propellant, its characteristics, its safe handling or transfer, potential damage to equipment or the environment, and the countermeasures for limiting the consequences in case of an accident. So a person, whoever it may be, which is going to handle the propellant, has to be trained very well in all the aspects covering about the propellant. They must also understand the potential hazards to the health of personnel, first aid, remedies in case of contact exposure of the skin, ingestion or inhaling, and the use of safety equipment. So they should be trained with all things when they are dealing with the liquid propellant. The next, some examples of safety equipments are protective clothing, face shields, detectors for toxic vapors, remote controls, warning signals or emergency water deluge. So all these safety features has to be carried out when any personnel is dealing with such kind of toxic liquid propellants. Then the personnel working with or being close to highly toxic materials usually have to undergo periodic health monitoring. because continuously working in such an environment can be very dangerous for someone's health. Then most organizations have one or more safety specialists who review the safety of the test plans, manufacturing operations, designs, procedures, or safety equipment. So, safety specialist has been installed in one of the two organizations everywhere to take care of such safety or environmental hazards. Then, with the proper training, equipment, precaution, and design safety features, all propellants can be handled safely. It is not that every propellant is very harmful and it is very dangerous to handle such propellant. If we are given with proper precautions and training and with such all safety features, we can be safe with the propellants and we can make more use out of it for our applications. So today the type and amount of gases and liquid discharges are regulated and monitored by government authorities. So to manufacture any propellant, there might be some gases and liquid discharges. The management of all these discharges has been controlled by the government authorities and they take care of such all factors. The next thing we will discuss is about propellant tanks and feed systems. So the propellant feed has two principal functions. That is, it has to raise the pressure of the propellants and it has to feed them at predicted mass flow rate to one or more thrust chambers. So the feed systems just have two particular reasons for their operation. That is, they have to raise the pressure of the propellants when they are stored in the tanks. They have to maintain that pressure. And second is that they have to feed them at predicted mass flow rates to the thrust chambers which are available for the combustion. So the energy for these functions comes either from a high pressure gas, centrifugal pumps, or a combination of the two. So there's some energy required to function these feed systems and it comes usually from a high pressure gas, centrifugal pumps, or a combination of two. Mostly there are two types of feed systems which we will discuss today. That is, first one is pressurized feed system, then turbo pump feed system. So how to select which feed system is necessary for our application? So there is some selection criteria of a particular feed system and its components which is governed by the application of the rocket, the requirements which we have, the duration, number or type of thrust chambers available, then past experience, the mission, simplicity of design, ease of manufacture, low cost, minimum inert mass. So these are certain criteria based on which we can decide which feed system and its components should be selected for our application. First, we will discuss about gas pressure feed system. It is one of the simplest and most common means of pressurizing the liquid propellant, where the liquid propellants is to force them out of their respective tanks by displacing them with high pressure gas. So this is a typical gas pressure fed system. So here we can see two separate propellant tanks are provided. One is for fuel and other one is for oxidized. And the pressurized gas is stored inside the propellant tanks at a certain level. So the main objective of this gas pressure fed system is to force the liquid propellants out of their respective tank to the thrust chambers by displacing them with the high pressure gas. So you'll see the working process, that is how it happens. So after all tanks are filled, the high pressure gas valve is remotely actuated and admits gas through the pressure regulator at a constant pressure to the propellant tanks. So when the tanks are filled, a high pressure gas valve is actuated and allows the high pressure gas to enter inside the tank through the pressure regulator. Then the check valves prevent mixing of oxidizer with the fuel, particularly when the unit is not in an upright position. Then the propellants are fed to the thrust chamber by opening appropriate valves. So we can see in the figure that with the help of such check valves, the fuel and oxidizer are allowed to move into the thrust chambers with opening of some of the valves. And when the propellants are completely consumed, the pressurizing gas can also scavenge and clean line and valves of much of the liquid propellant residue. And when all of the gas has been consumed into the thrust chamber, then this high pressure gas can be used to scavenge the tanks to get it clean. So this is how the gas pressure fed system works. So this system gives a vehicle performance superior to a turbo pump system when the total impulse or the mass of propellant is relatively low, the chamber pressure is low, the engine thrust to ratio is low, and when there are repeated short duration thrust pulses, the heavy walled tanks for the propellant and the pressurizing gas usually constitute the major inert mass of the engine system. So these are some of the applications where the gas pressure fed systems are used, such as when we need low total impulse and low chamber pressure. So there are major two types of gas pressure fed system. That is, one is regulated pressure system and blow down system. The comparison for both is given here is that for first one, the pressure of the thrust it remains constant. For blow down system, it decreases when the propellant is getting consumed. The storage of gas in both of the systems is different, that is in regulated pressure. They are stored in separate high pressure tanks, while in blowdown system they are stored into the propellant tank, as how we discussed in the previous slide. The advantage of using regulated pressure is that constant propellant flow is managed, so approximately it gives constant thrust. And for blowdown, the advantage is that it is a very simple system and less gas is required. This is obvious because gas is stored within the propellant tanks itself. Then the disadvantage for regulated pressure system is that regulator is present, so it will introduce a small pressure drop which will give shorter burning time. While the disadvantage for a blowdown system is that thrust decreases with burn duration and higher residual propellant is available. These are the two gas pressure fed systems used in today's rocket engines. Now we'll discuss turbopump fed systems. The propellants are pressurized by means of pumps, which in turn are driven by the turbines, which derive their power from the expansion of warm gases. So this is the loop in which this turbopump fed system runs. That is, the power derived from the expansion of warm gases that drive the turbine, which is used to pressurize the propellants using pumps. So it is a high precision, accurately balanced piece of high shaft speed rotating machinery with usually two or one centrifugal pump and a turbine. So a pump and a turbine system is used to pressurize the gas into the propellant tank. So it has shaft seal to prevent leakage of propellants and also to prevent the two propellants from mixing with each other inside the turbopump. So all the safety features has been taken care of when a turbopump fed system is used. Then engines with turbopumps are preferred for booster and sustainer stages of space launch vehicles, long range missiles, and in the past also for aircraft performance augmentation it was used. So these are the applications where turbopump fed systems are used. Moving on to the next part, that is turbopump fed systems are usually preferred when the engine has a relatively high total impulse, which means high thrust and long duration. So earlier we have seen that the gas pressure fed systems they were used for low chamber pressure, low total impulse application, while as this heavier turbopump fed systems are used where we need very high thrust and long duration of flights. Pressurized fed systems which we discussed earlier are best for rocket engines with relatively low total impulse, that is low thrust, and often low cumulative firing durations. While in a turbopump fed systems, the propellant tank pressures are much lower by a factor of 10 to 40, and thus the vehicle's tank masses are much lower, again by a factor of 10 to 40. Then turbopump systems usually gives a superior vehicle performance when the total impulse is large and the chamber pressure is high. So each system have its own advantage and disadvantage based on their applications. So these are the comparison for turbopump and gas pressure fed systems. So next we will see is propellant tanks. So till now we have discussed the fed systems which use this tanks. So we'll see what all these tanks are. So in liquid bipropellant rocket engine systems, the propellants are usually stored in an oxidizer tank and a fuel tank within the flying vehicle. So we have seen in the figures as well, the two separate tanks are provided when a bipropellant is used. Well, when you are using a monopropellant, then a single tank will be used in which the desirable feed system can be used. So there are usually also one or more high pressure gas tanks, the gas being used to pressurize the propellant tanks. So we have seen in gas pressure fed systems for the regulated type that separate tanks are provided for the high pressure gas tank. So these tanks can be arranged in a variety of ways, and the tank design, shape, and location can be used to exercise some control over the change in the location of the vehicle's center of gravity. So there are these factors which has to be taken care of when we are selecting a propellant tank. This is because the propellant tank has to fly. Its mass is at the premium and the tank material is therefore highly stressed. This is the important area where we have to focus when we are selecting a propellant tank, because it is the area where high stresses will act because there is a strong pressurization system connected. So the common tank materials are aluminium, stainless steel, titanium, alloy steel, and fiber reinforced plastics with an impervious thin layer liner of metal to prevent leakage through the pores of the fiber reinforced walls. So composites are being used in propellant tanks as well, and every single detail has been taken care of. That for reinforced plastics we know that there are some of the pores, so the leakage should not happen. So a thin inner line of metal is provided for such composites such that the propellant does not leak through this tank walls. Then we will see the various configurations available for propellant tanks are present here. So the spherical tanks, then tandem tanks with common bulkhead with external piping, internal piping, then concentric tanks and multi-tank. So in multi-tank we can see that 6 fuel tanks are used and 3 oxidizer tanks are used. So these are the different propellant tank configurations used in today's world based on the different applications. The most optimum shape of a propellant tank and also a gas pressurizing tank is spherical because for a given volume it results in a tank with the least weight. That is correct because a spherical volume can give you a least weight, but the larger spheres which are needed for the principal propulsion systems are not very efficient for using the space in a flight vehicle. So at that time, different configurations took place are used for different types of applications. So some of the categories of using this propellant tanks based on the feed systems which we are using today is present here. For pressurized feed systems, the average pressure values reach from 1.3 to 9 MPa. Then for high pressure gas, which is used to expel the propellants, the pressure value reaches from 6.9 to 69 MPa. While for the turbopump feed systems, which are used to suppress the pump cavitation such that will pressurize the propellant tanks lightly, the pressure used is very low, that is it is around 0.07 to 0.34 M. These are the various category of propellant tanks which we see today in rocket propulsion applications. So this covers the propellant tanks and the fed systems which are used in rocket propulsion. Next we will move on to combustion process. So the combustion process behavior is propellant dependent. So based on what propellant is, how it is behaving, even the combustion is varied based on that. The objective of a combustion process is to operate at very high combustion efficiencies and to prevent 100% of all the occurrence of destructive combustion instability. This is the objective for any combustion process happening. Either it may be an aircraft engine or a rocket engine. It should work with 100% efficiency and there should be no combustion instabilities present. The efficiencies of 95 to 99.5% are typically compared to turbojets or furnaces which can range from 50 to 97%. So this is due to the very high reaction rates at high combustion temperatures and the thorough mixing of fuel and oxidizer reaction species by means of good injection flow distribution and gas turbulence. And the losses are largely due to incomplete burn or inadequate mixing, that is non-uniform mixing ratio. So the thrust chamber should operate with stable combustion over their full range of operating conditions. So this is a must that the thrust chamber should operate with the stable combustion with their overall function during the flight. So for very small bipropellant thrust chambers or small gas generators where the injector has very few injector orifices or elements, the combustion efficiency can be well below 95%. We have seen this that how this happens. Then the combustion process is usually analyzed as a steady flow process, but in reality it is not so. Because when observing any one location within the chamber, one finds a turbulent flow with local fluctuations with time in pressure, flow, temperature, density, mixture ratio, or radiation emissions. The combustion process is never a steady state flow. It is always a transient flow which involves many complexities and which are very hard to analyze and solve. So the combustion process which we see, it occurs at various zones. So here in figure we can see this is typical combustion process happening in the thrust chamber and the nozzle. So different combustion processes, they happen at different zones, such like the injection and atomization process happens at the injection atomization zone. So the first left which we see in the figure, in that region this process happens. The next one is vaporization and mixing and reaction, which happens in the rapid combustion zone, which is the second one, and the last one is expansion in chamber, so it happens in string tube combustion zone. So these 5 processes constitute the combustion process for a liquid propellant rocket engines, and these 3 happens in 3 different zones, which are outlined below. So we'll discuss each of this process in brief, that is what they constitute for. So in the injection process, the liquid jets or the sprays which are used enter the chambers at relatively low velocities. So this injection is nothing but of liquid oxidizers and liquid fuels. They are entered as sprays or small jets through injector orifices. Then the second process is atomization, where secondary breakup of droplets or the formation of droplet begins. In vaporization phase, the droplet gasification and diffusion happens, and further heat release from local chemical reactions is happening. So from here the combustion starts, that is in the rapid combustion zone. First there will be droplet gasification and diffusion. So the molecules will start to diffuse and further heat release will be there from local chemical reactions. Then mixing and reaction will begin, that is 3D turbulent mixing will begin, and multiple chemical reactions and major heat releases will happen in this process. Then after the combustion is done, it has to be expansion. So the flow moves towards the nozzle and there is heat transfer to the walls. So acceleration to high chamber velocities happens in this last procedure. So we'll discuss how these processes happen in each of these zones. The first zone, that is injection atomization zone. So two different liquids are injected, both with storable bipropellants and on liquid oxygen hydrocarbon combinations. And they are injected through orifices or slots at velocities typically between 7 and 60 meter per second. So the fuel and oxidizers are injected through orifices or slots at velocities typically between these, that is 7 or 60 meter per second. The injector design has a profound influence on the combustion behavior, and some seemingly minor design changes can have a major effect on instability. So some of the injector parameters, that is the pattern, sizes, number, distribution and types of orifices, influence the combustion behavior, as do the pressure drop, manifold geometry or surface roughness in the injection orifice walls. So the injector plays major role in combustion behavior because it is the first zone in which the liquid fuel and oxidizers are entering. So in this first zone, the liquids are atomized into a large number of small droplets. So when the liquid fuel and oxidizer are entering into this injection zone, they are broken down into small droplets, and heat is transferred to the droplets by radiation from the very rapid combustion zone and by convection from the moderately high gases in the first zone. The droplets evaporate and create local regions rich either in fuel vapor or oxidizer vapor. Then from here the vaporization process starts, and in rapid combustion zone, intensive and rapid chemical reactions occur at increasingly higher temperature, and remaining liquid droplets are vaporized by convective heating, and gas pockets of fuel-rich and fuel-lean gases are mixed. The mixing is accomplished by local 3D turbulence and diffusion of the gas species. So the mixing has to be happening properly such that it should not be a lean combustion, it should not be a rich combustion. Then the further breakdown of the propellant chemicals into intermediate fractions and smaller, simpler chemicals and oxidation of fuel fractions occur rapidly in this zone. This all process happens within very short amount of time. That's why it is called as rapid combustion zone. So next, when the chemical reaction is done, it has to come into steam tube combustion zone. So in this zone, oxidation reaction continue but at a lower rate, and some additional heat is released. So the oxidation reaction rate is reduced here. However, chemical reactions continue because the mixture tends to be driven towards an equilibrium composition. The actual velocities are very high, that is 200 to 600 meter per second, and the transverse convective flow velocities are relatively small in this stream tube combustion zone. So the transverse velocities are getting reduced and the axial velocities are getting very high in the range of around 200 to 600 meter per second. The streamlines are formed and there is relatively little turbulent mixing across streamline boundaries. So the combustion is done and the oxidation reaction rate is getting reduced and axial velocities are getting accelerated in this zone. Streamlines are formed and relatively little turbulent mixing occurs in this region. The residence time of the propellant material in this zone is very short compared to the residence time in the other two zones, which is usually less than 10 milliseconds. So the residence time is nothing but the time the propellant stays in that zone, propellant resides in that zone. So compared to injection atomization zone and rapid combustion zone, the residual time for steam tube combustion zone is very less, that is less than 10 milliseconds. The combustion in a liquid rocket engine is very dynamic, with the volumetric heat release being approximately 370 megajoule per meter cube second, which is much higher than in turbojets. The volumetric heat release is very much high as compared to turbojets. That's why the liquid propellant rocket engine has a dynamic combustion. So once it covers this stream tube combustion zone, it goes through the nozzle and thrust forces generated with all the processes we discussed. Moving on to the next slide, we will see how we can analyze and how we can use this in our simulation to understand the combustion process very well. So for the purpose of analyzing the combustion process and its instabilities, it has been convenient to divide the acoustical characteristics into linear and non-linear behavior. So to analyze the combustion process and to understand it very well, the acoustical characteristics has been classified into linear and non-linear behavior. A number of computer simulations with linear analysis have been developed over the last 45 years and have been used to understand the combustion process with liquid propellant combustion devices and to predict combustion oscillation frequencies. So linear analysis can be done with the computer simulations available today, but the non-linear behavior, for example, why does a turbulence cause an apparently stable combustion to suddenly become unstable, is not well understood and not properly simulated yet. So to analyze this non-linear behavior, mathematical simulations require a number of assumptions and simplifications to permit feasible solutions. Good models exist for relatively simple phenomena such as droplets of a propellant vaporizing and burning in a gaseous atmosphere, or the steady-state flow of gases with heat release from the chemical reaction. But again, it requires skilled, experienced personnel to use, interpret, and modify the more complex programs so that meaningful results and conclusions can be obtained. So there are the following phenomena which are usually ignored or practically simplified when they are dealt with non-linear behavior analysis. So cross-flow is the phenomenon, then non-symmetrical gradients, then unsteadiness of the flow, which includes time variation in the local temperature, local velocity, then next local gas composition, thermochemical reactions at local off-design mixture ratios and at different kinetic rates, enhancement of vaporization by acoustic fields, uncertainties in the spatial as well as the size distribution of droplets from sprays, then drag forces on droplets. So all these phenomena are being ignored when the nonlinear analysis is carried out. So the computer programs which are available, which we discussed, the outputs of these computer programs can give valuable help and confirmation about the particular design and are useful guides in interpreting actual test results. But by themselves, they are not sufficient to determine the designs, select specific injector patterns, or predict the occurrence of combustion instabilities. So this is when the computational fluid dynamics helps. So CFD is a relatively new analytical tool that can provide a comprehensive description of a complex fluid dynamic and thermodynamic behavior. It allows for a time history of all parameters and can even include some nonlinear effects. So numerical approaches are used to evaluate sets of equations and models that represent the behavior of the fluid. So this is how the computational fluid dynamics works. Numerical approaches are used to evaluate certain sets of equations and models that represent such behavior of the fluid. It has been applied to resonance cavities in injectors or chambers and to the flow of burning gases through turbines. Then a comprehensive rocket combustion model using CFD is not yet available but could become useful in the future. So slowly the trends are getting more close to the CFD and more evolution is happening in this field. So one day the complete model for modeling a rocket engine will be available, which will be very useful in future. So for the complex geometries, the information has been tracked with more than 150,000 discrete locations and can include changes in gas composition, thermodynamic conditions, equilibrium reactions, phase changes, viscous or non-viscous flow, 1, 2 or 3-dimensional flow and steady state or transient conditions. So this all is included into the computational fluid dynamics, and slowly it is getting more close to a complete rocket combustion model. Moving on to the combustion instabilities. So none of the systems has worked to the 100% of the capacity, and there are always some limitation, or there is always 0.001% of chance of the system not working appropriately as designed. So even the combustion process happening in the rocket propulsion system can face the instability. So if the process of rocket combustion is not controlled by a proper design, then combustion instabilities can occur which can very quickly cause excessive pressure vibration forces which may break engine parts, or excessive heat transfer which may melt thrust chamber parts. So these combustion instabilities, they can create excessive pressure vibration forces or excessive heat transfer which can either break the engine parts or can melt the thrust chambers. So admittedly, combustion in a liquid rocket is never perfectly smooth. Some fluctuations of pressure, temperature, and velocity are always present. So when these fluctuations interact with the natural frequencies of propellant-fed systems with and without vehicle structure, or the chamber acoustics, periodic superimposed oscillations recognized as instability occur. So when these fluctuations they interact with the natural frequencies of the propellant fed systems, then the instability can occur. So in normal rocket practice, smooth combustion occurs when pressure fluctuations during steady operation do not exceed about plus minus 5% of the mean chamber pressure. So this is the evaluation criteria given for when the combustion instability can occur or not. Then combustion that gives greater pressure fluctuations at a chamber wall location which occur at completely random intervals is called as rough combustion. So greater pressure fluctuations at the chamber wall can create completely random intervals, completely random instability is called as rough combustion. Unstable combustion or combustion instability displays organized oscillations occurring at well-defined intervals with a pressure peak that may be maintained, may increase, or may die out. So, an instability can display as an organized oscillations occurring at a well-defined intervals with a pressure peak which may increase, which may die out, or which may remain constant. So, we'll discuss major types of combustion instability. So, there are three types of combustion instabilities in rocket propulsion, of which they are first is chugging, then buzzing, then screeching or screaming. So in the first one, it stems mostly from the elastic nature of the fed systems and structures of the vehicle or the imposition of propulsion forces upon the vehicle. It can be caused by resonances in the engine fed system, such as an oscillating below inducing a periodic flow fluctuations or a coupling of structural and fed systems frequency. So this chugging instability it is mainly caused by the resonances in the engine fed system or a coupling of the structural and feed system frequencies. It is not considered as a much destructive type of instability, but still it can cause harm for the engine systems. The next one, that is buzzing, seldom represents pressure perturbations greater than 5% of the mean in the combustion chamber and usually is not accompanied by large vibratory energy. It often is more noisy and annoying than damaging, although the occurrence of buzzing may initiate high pressure instability. Often it is characteristic of coupling between the combustion process and flow in the portion of propellant fed systems. So this is the major problem when we are dealing with the liquid propellant rocket engines is that a separate propellant fed systems is used. So when frequencies of this fed systems is interacting with the combustion process or is interacting with the structural frequencies, then this instabilities come into the picture. So this buzzing instability is not much damaging, but it is very noisy and it is very annoying. And the last one, that is screeching or screaming, it has high frequency and is most perplexing and most common in the development of new engines. Both liquid and solid propellant rockets commonly experience high frequency instability during their development phase. Since energy content increases with frequency, this type is the most destructive, capable of destroying an engine in much less than 1 second. So the engine components itself starts harming the complete engine. That is when the instability starts to occur and it can destroy this in less than 1 second. These are the three types of combustion instabilities present in combustion process of rocket propulsion system. So we'll discuss how we can control this combustion instabilities. The designer usually relies on the prior experience with similar engines and tests on new experimental engines. And the analytical tools are available with which to simulate and evaluate the combustion process. So these analytical tools can be used prior. The experimental tests and simulation results can be used to eliminate the combustion instabilities. The design selection has to be proven in actual experiments to be free of instabilities over a wide range of transient and steady state operating conditions. So before going to the experimental phases, the design phase should eliminate all the combustion instabilities dealing with the steady state or transient conditions. So some of the experiments can be accomplished on a subscale rocket thrust chamber that has a similar injection, but most tests have to be done on a full-scale engine. Then the control or really the complete simulation of instabilities and an important task during the design and development of a rocket engine. Yes, it is a very important task during the design and development of a rocket engine because all the hard work which has been done to fly a rocket engine into the space, it may get destroyed within a second if a single instability starts to occur. So it is better to recognize these all instabilities in the design phases itself and not to take them directly into the experimental or the flight test. The design features to control instabilities are different for three types of vibration. So these three instabilities which we discussed, so each of these instabilities they have their own design features which has to be taken care of, and they should be compatible with each other. They should be compatible with the mission requirements, the application which we want the system to do, etc. Moving on to the next slide. So use of data from prior successful engines and simulation programs to establish key design features and estimate the likely resonances of the engine and its major components. So using the prior experience data which is available and with the help of simulations, all these instabilities has to be estimated by understanding where the resonance of the engines and its major components is happening. Then we can slowly eliminate these instabilities by doing some of the minor changes in the components from where the instabilities are getting initiated. Then design the feed systems and structures to avoid such resonances. Use a robust injector design that will provide good mixing and dispersion of propellants and be resistant to disturbances. So we have seen that a good injector design is very much important such that no any other vibrations or energies are created in further combustion process which can cause for a resonance and then further an instability. If needed, include tuned damping devices such as cavities to overcome acoustic oscillations. So some cavities can be used to eliminate some of the vibrational oscillation. So to validate that a particular thrust chamber is stable, it is necessary to test it over the range of likely operating conditions without encountering instability. So number of tests has to be carried out for changing operating conditions for a particular thrust chamber which has to be stable. Then an analysis is needed to determine the maximum and minimum likely propellant temperatures, maximum minimum probable chamber pressures, and the highest and lowest mixture ratios during a propellant budget. So using a propellant budget, all these things has to be estimated in the design and development phase itself. So these limits then establish the variation of test conditions for this test series. So these all things can be used to establish the variation of test conditions for the test series to eliminate the combustion instabilities. So this is how we can eliminate combustion instabilities using prior experience, various simulation data, and varying different test conditions, operating conditions, using some of the cavities to eliminate the oscillations, etc. So the summary for today's class is that first we have discussed fundamentals of liquid propellant rocket engines, which included the process, how it is done, and the various components included, advantages, disadvantages of using such kind of system, and the classification based on several factors. After that, we have seen different types of liquid propellants with their features, examples, advantages, applications, and limitations. So the liquid propellants which we have saw are monopropellants, bipropellants, cold gas, cryogenics, storable, gel, and hybrid propellants. Then we have discussed each of the propellant with its features, examples, advantages, disadvantages, and applications. Next, we saw various desirable physical properties of the liquid propellants, that it should have low freezing point, high specific gravity, chemical stability, ignition, combustion, and flame properties required. Also, we saw various factors like economic factors, propellant performance factor, and the physical hazards which define propellant property combination when selecting a propellant combination. Then we have seen how we can use additives to tailor or alter some of the properties of the propellants. Again, various safety and environmental concerns of using liquid propellant rocket engines we have seen that we have to use face shields, protective clothing, etc. to protect personnel who is engaged in using the liquid propellant at the site. Then two different propellant feed systems we have discussed, that is pressurized feed system and turbopump feed systems with their various selection criteria. So under pressurized feed systems we have discussed the working process, how different valves are used and where the gas is stored. Based on that, two different types are provided under pressurized fed system, that is regulated pressure and low down system. Then we have seen the comparison that how these two have their own features and their limitations as well. Then we have discussed turbopump fed systems with its features, advantages, applications and limitations. So the turbopump fed systems, they are mostly used where the application which we have needs high total impulse and high thrust, which also provides less tank size. Then we discussed about different configurations of propellant tanks, their features and categories, and why the spherical tank configuration is more suitable but also has a disadvantage when we go for multiple operations. Then we have discussed combustion process in very detail, which is propellant dependent. So we have seen processes like injection, atomization, vaporization, mixing and reaction, then lastly expansion happening at various zones like injection atomization zone, rapid combustion zone and steam tube combustion zone. So we have seen step-by-step process of how this combustion happens in a liquid propellant rocket engine. Then after that we have discussed about how we can carry out the analysis of this combustion. So analysis of combustion process using different tools like mathematical models, analytical tools like CFD, and the phenomena which are ignored like cross flow, non-symmetrical gradients, local gas composition, etc. Then we have seen that why this analysis is very important, because if they are not handled very carefully, then combustion instability occurs in the propulsion system. So how this combustion instability is initiated and the three different types of instabilities we have discussed, and what measures we have to take care when we are dealing with the combustion instability is discussed. This finishes this video about liquid propellant rocket engines, and these are the references for today's class. In next class, we will start with solid propellant rocket engines. Thank you.